All right, folks, back again. Um, Hope everybody got caught up on their week of catching up. Um, we're going to go to 06 here, multiplying probabilities. Now, the other probabilities we were doing, they were ors. They were this or that happening. Well, this is going to be an and. Want two things to happen. Okay, two different criteria or two different events. Okay, so the first thing we're going to do is we're going to look at independent events. All right, now independent events means the occurrence of one event does not affect the probability of a second event happening. Okay, so in other words, if I was flipping a coin and rolling a die, one has no effect on the other one. Those would be an example of independent events. Um, Flipping a coin twice in a row, one has flipping that coin the first time has no effect on what happens the second time I flip it. Those are independent events. So when I'm looking at two different things happening, the probability of A and B, okay, and sometimes that's written with an intersection. Um, Sometimes it's written like this, just so you know. Okay, that equals the probability of A times the probability of B, as long as they're independent events. Okay, because like I said, we're gonna let's do this the simplest one I can think of. Let's go. We're gonna say we're gonna flip a coin. Okay, and we're gonna roll a six-sided die. All right. So what I want is the probability that when I flip the coin, I'll get a tails. And when I roll the die, I will roll a 4. Now, I think it's pretty simple to see that those are obviously independent. Flipping a coin has nothing to do with rolling the die. So I just take each probability. So I want to know the probability of tails times the probability of rolling a 4. All right, those are independent, so I can just multiply them. So, probability of getting a tails when I flip a coin is 1/2. Probability that when I roll a single die that it'll come up with 4. There's 6 sides to it, 6 numbers, 1, 2, 3, 4, 5, 6. So that's 1/6. Multiply them together is 1/12. So, and then I can change that to a decimal or percentage or whatever. All right, so that's what independent events are. The multiply each single probability. They have nothing to do with each other. Okay, nothing to do with each other. And then on the obviously the flip side would be dependent events. Okay, dependent events all right, that's when just the opposite. The occurrence of one event does affect the probability. Make sure I use the right affect, not effect. The probability of the second. Okay, so let me explain to you or give you an example of that. All right, let's say that I am going to go back to our deck of cards, our standard deck of cards, all right? And let's say I'm going to pick 2 cards, okay, out of the deck of cards, all right? And we're not going to do a replacement. In other words, we're not going to put it back in the deck. I'm going to pick a card, hold it, pick another card, okay? So that we're going to call that no replacement. That's usually what it says, all right? All right, so I want a probability that when I pick 2 cards without putting the first one back, the probability that I can pick, let's say, a 3 and a queen. Okay, so when we're not putting it back in the deck. So if you remember, I don't know if you do, our deck of cards. Yes. 52 cards, 13 in each suit, 4 suits, blah, 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 blah. Okay. So I want to know the probability that I can pick a 3 and a queen. Now this is no replacement. So I can't just, so they're affecting each other. Because when I pull out a 3 and I pull out a card and I hold it, there's less cards. So that affects the next card. So that's why these are dependent. So you can't just multiply. All right, you can't just multiply the two together. So you have to figure out how it affects it. So the probability that I could draw a 3, just let's say what's probability I reach in and draw a 3? Well, there's 52 cards. And there's 4 3s, right? I only want one of them. But that's what I want is there's 4 of them, and there's a total of 52. Okay, and then I'm going to multiply that by the probability that I will draw that queen. Now, there's no longer 52 cards. I pulled a card out of there. That's why this affects it. It's dependent. So there's still 4 queens, but now there's only 51 cards. Okay, that's the difference in those two things. This pulling that card out affects the next probability. So I do the math. Let's see, that would be, let's reduce this first. 4 goes into 4 once, into 52 13 times. So that would be 4 over 663, which is approximately, my alarm going off. So that's approximately 0.6%. Now, if you're not one of those people that like to do the simplifying first, I believe we would have got 16 over 2652, and that's still going to be the same answer. So you have a 0.6% probability of when you pick 2 cards at random from a deck of cards that you'll draw a 3 and then a queen. Okay? All right. All right. So dependent events, that kind of brings us to the next step in this, which is conditional probability. So conditional probability is based on a condition. So it's the probability of one event happening given that another event has already happened. So the probability that I will get that queen given the fact that I drew the 3 already, or something like that. And I'm going to do examples. But you write it like this. Probability of B/A means what is the probability of B happening given that A has already happened. Okay, so if you remember, so for dependent events, now we don't do this for independent because independent, they don't have any influence over each other. So kind of a way to sum up what I did on that last problem. So the probability of A and B happening, all right, is the probability of A times the probability of B given that A already happened. So that's what we did on those cards. So I took the probability of getting a 3 was 4 out of 52, and then I wanted the probability of getting a queen, which means the probability of getting a queen given that I already got the 3, and that's why we subtracted 1 from the total because we're assuming we got that. That's dependent probability given a condition. Okay, so let's say the old go-to probability problems, bag of marbles with different colored marbles. Okay, and let's say we've got 12 red. If I wasn't doing the video, I'd probably change my pen colors and use exact pen colors, but trying to save a little time here. 9 blue, 11 pink, and 12 green. Okay, these are all in a nice little bag for a total of 44. All right, so I want to know what is the probability that I can pull a red marble and then a blue marble. Okay, and once again, it's important to tell you that there will be no replacement. So I'm not putting the marble back in the bag once I draw it out. Okay, so these are dependent events, and I'm trying to find the probability of red and blue. All right, so what that really means, if we put it in this form up here, all right, so we want the probability of drawing a red okay, times the probability of drawing a blue, given that I've already drawn the red. All right, that's what we're doing there. All right, so it's much easier than it seems. Drop my pen, hold on. All right, so the probability of getting a red. Well, there's 12 red, all right, out of a total of 44. So boom, got my red. Now this says the probability of getting a blue, that you've already got the red. So blue, there's still 9. But given the fact that I pulled out a red and not put it back, there's now only how many marbles there? 43. That is correct.
That was easy.
Okay, so then we do our math. You can do shortcuts, whatever you want to do. Some of you don't like to simplify first, so that would be 108 over 1892. Reduce that, use your calculator, whatever. Or it might ask you just for a decimal answer. So that would be 0.057 or roughly 5.7%. Okay? All right. So conditional probability. Let's kind of recap what goes on. These are, you're doing two different things, and one is based on the other one happening. So conditional probability. Now, there is a little formula for it. Guys, it doesn't matter if you use a formula, if you get it just by doing it like we did here. Now, if I were to put the marble back in the bag, then this would not be conditional because you're putting it back in. So it would just be 12 over 44 times 9 over 44. It wouldn't be any different. Okay, so conditional probability, go back up here to this guy. The probability of B given A can be written as the probability of A and B happening divided by the probability of A. And these can switch around, guys. You know, we're just using the letters. Sometimes you'll see this written, like I said, for and, A intersect B divided by the probability of A. So it means the same thing. Intersection is and. Okay, so that's a formula we can use if we're giving some different things happening. We can plug those values in. Now, just for the record, you know two things are independent if, and this will kind of be, I hope felt, kind of self-evident, if the probability of B given A equals the probability of B by itself, then that tells me that A and B are independent because one didn't influence the other. I don't get that, Miss French. So if the probability of B is exactly the same as the probability of B given that A happened, that means that A didn't influence the other one, or B didn't influence A, however you want to look at it. It means they're independent. Okay? So you might run into problems where they ask you that. I can't see that, French. Why don't you bring that up? So let me go back over that because dumb me didn't look at the screen. So if you're asked, are two things independent, and they don't tell you, if you find the probability of whatever B is by itself, and then you go ahead and you find the probability of B given that A happened, and those two are equivalent, then you know that they're independent. Okay, that's what that is saying. All right. All right. So for our last problem here in part one, um, is going to show you how the probability works with the conditional probability. So here's an example. It says at a restaurant, 25% of customers order chili. So it means of all the customers that come in, 25% of customers order chili. And then it was determined also that 4% of customers order chili and a baked potato. So they want to know, what is the probability that someone who orders chili also orders a baked potato? Now, you can't say, oh, it's 4%. No. These are two separate things. One is 25% of customers get chili. The other one is 4% of the customers who order chili also order a baked potato. All right, so if we break these down into something to make it a little simpler, if we look at this, we can say A is that a customer orders chili. Okay, so A is orders chili. All right, and let's say B is orders a baked potato. Okay, so we want, so now we don't have that particular one. We have orders chili, and we've had customers order chili and a baked potato. So we have A and B. A and B would be orders chili and baked potato. Potato. I don't know. It's either a potato or a potato, or a jalapeno or a jalapena. I don't know. It doesn't matter. You call it what you want to call it. All right. So once we can assign these things, it's a little easier. So we're trying to figure out, what is the probability that someone who orders chili also orders a baked potato? So what we're trying to find out is the probability of B given A. We want to know, what's the probability that someone who orders chili also orders a baked potato. So we're trying to figure out the probability of B. So probability of ordering the potato, right? Because that's what that is. Given A. So that's potato. That's chili. And that's what that question is asking. What is the probability that someone who orders chili will also order a baked potato? Okay, so probability that someone's going to order a potato given the fact that they ordered chili. So if we do our little formula from before, that's the probability of A and B divided by the probability of A. Well, we have those things, believe it or not. The probability of A and B, chili and baked potato, is 4%. Okay, we were told that. We were given that information. So chili and baked potato, A and B, is 4%. We were already given that. So that's a 4%, or a 0.04. Okay, we're also given the probability of someone that orders chili. That's the 25%, or 0.25. So if I'm doing this problem, the probability of A and B happening, we already have it. It's 4%, because it says 4% of customers who order chili and a baked potato. So that's 0.04. And then the probability of people ordering chili is 25%, or 0.25. You do the math, you get 0.16. So the answer is, what's the probability that someone who orders chili also orders a baked potato? 16%. You might scoff at that, but with this whole semi-quarantine and stuff at home, I've had a baked potato with chili and cheese on it. I'm not going to lie. It's pretty good. Pretty good. All right. I think that's good for this part of the lesson. Now, I'm not going to give you assignment until I do the second part, okay? So, no assignment on this part. I'm going to do the second part right after this, and then I'll give you the page that the work's on and stuff. because I got to do a little chart and show you guys how to do a two-way table. All right, so that's coming up next, folks. Till then, bye-bye.